Number 12. Y is equal to sine x, where x is measured in radians. Use differentiation from first principles to show that dy by dx is equal to cos x. You may use without proof the formula sine of a plus or minus b. Assume that as h tends towards 0, sine h over h tends to 1, and cosine h minus 1 over h tends to 0. So in order to find dy by dx by first principles, as the limit of h tends towards 0, we use the formula f of x plus h minus f of x over h. So in this case, our f of x is sine x, so we are going to write this as sine of x plus h, take away the sine of x over h. Because the sine of x plus h is an addition formula, and the question also says that we can use the addition formula for sine of a plus or minus b, we can use our trigonometric identity for the addition formula, which is also given in the formula booklet, and we can expand that as sine x cosine h plus cosine x sine h minus sine x over h. We can now write this such that all the sine x values are written as a single fraction, and all the cosine x values are also written as a single fraction. So we can write this as sine x cosine h, take away sine x over h, plus cosine x sine h over h. In the first term, we can now factorize the sine x to give us sine x brackets cosine h minus 1 over h, and in the second bracket we can factorize cosine x to give us plus cosine x brackets sine h over h. Because the question says we can assume that as h tends to 0, sine h over 1 tends to 1, and cosine h minus 1 over h tends to 0, we can see that we've now got that in the equation, and we can just substitute 1 and 0 respectively. So as h tends towards 0, dy by dx will now be equal to sine x, and the value that they've given for cosine h minus 1 over h is 0, so we can replace that with 0. And the value that they've given us for sine h over h is 1, so we can replace that with 1. Sine x multiplied by 0 would just be 0, so this would now just be equal to cosine x.